Okay, we have a scary looking integral on the board here today with a lot of logs integrating from 7 to 3. And at first it does look kind of impossible, but the thing is, like, if you're given a problem that looks impossible, it's probably possible unless someone's really messing with you. I think the key to this whole problem is recognizing that this is actually something that can be solved using the King's principle. Without going into all the details of this, what we're basically looking at is something where, notice the two bounds 7 and 3 add up to 10, so we can make an interesting u substitution that's going to make this work, where we actually end up making a copy of this whole integral. So let's just jump right into what the u substitution is. So what we're going to do is, for our u, we're going to add the bounds. So 7 and 3 is 10 minus x, just recognizing that this here is going to be our u. But then you might think, okay, that's going to make it more complicated, because we simplify this piece, but we make this more complicated, and that's kind of true, because x is going to be, just rearranging this, x is going to be 10 minus u, and then our dx is going to be minus du. So then rewriting this, we're going to have, for our bounds, they're going to switch. Plugging 7 in here, we're going to get a 3, and plugging a 3 in here, we're going to get a 7. So we just flip the bounds, and that's what happens in these problems. Now let's write the numerator. Log 3, our x is, where's our x? 10 minus u. Okay, this piece is going to be exactly the same as what we have in the numerator, so it's going to be log 3, 10 minus u to the 8th, plus, and then this one's going to be simplified slightly, log 3 of u to the 8. But notice now that we have a minus, when we substitute for our dx, we end up with a minus on the du. We can bring this to the front, and we can use to switch our bounds of integration. So instead of going 3 to 7, we're going to rewrite this as 7 to 3, getting it back to what it was there. But this needs to become a plus sign. Now from here we can just do a change of variable, because in a definite integral the variable doesn't matter. We can call it whatever we want, but I want to call it x to get it to line up with our original integral. Okay, so now I've rewritten this, and all I've done is change our variable. No other change was made, so we just went to x. And the thing to notice now that's interesting is the denominator here is exactly the same as our denominator in the original integral. Okay, we just changed the order, but that doesn't matter because it's addition. So what that indicates, and what we're going to do, is we're going to add these two integrals together. Two copies. What we'll do, we'll call our original integral I, but this is actually the same integral, so this is also I. So if we add these two together, we're going to have two copies. We're going to have 2I, and then let's see what happens when we do that. So now we're adding the two copies together. I've indicated 2I for two copies of the integral. The only thing that kind of changed I made is I put this under one integral, because we have the same, because everything's under x, so we can do this all as one integral now, just adding them together. And then we also notice, because we have the same denominator, we can just add our numerator. But when we add our numerator, the key to the whole problem really is we're going to end up with the exact same thing that we have in the denominator, log 3x to the 8, log 3 10 minus x to the 8. And so everything's going to cancel, and this thing is just 1. So now, of course, if you got a simple integral, we're just going to integrate this. Integral of 1 is x, evaluated from 7 to 3 is just going to be 7 minus 3, which equals 4. But that's not quite the final answer, because we made two copies. We don't want to change that, so we need to divide both sides by 2, and we end up with a final answer of just 2. Kind of interesting that such a complicated problem is actually a really easy problem and can be solved very quickly once you can just recognize the pattern, and use this King's principle. I got this problem from my quiz, King's Rule Integrals. I'll provide a link in the description. Thank you for watching. Please like and subscribe. Have a good day.